Hello, my name is Linda and I'm a postdoc at the University of Toronto, and this is my poster presentation talk with the title Reconstructing Tumor Evolutionary Histories in Clone Trees and Polynomial-time with SubMARine. If you haven't seen my 8-minute main talk or are not familiar with reconstructing clone trees, I recommend watching the other talk first or having a look at my poster, because in this presentation I focus on how to build partial clone trees with validity rules. As a short repetition, there exist different methods that infer clone trees from subclonal frequencies. However, there are two key challenges. The first one is gaining algorithms to a large number of subclones, and the second one is efficiently representing uncertainty in a reconstruction that allows multiple clone trees to be equally plausible. In order to address these two challenges, we've developed SubMARine, a polynomial-time algorithm that builds partial clone trees. A partial clone tree defines a subset of the pairwise ancestral relationships between the subclones. It defines when a subclone is an ancestor or not an ancestor of another subclone. And it can also contain undefined relationships, when a subclone is a possible ancestor of another subclone. The notion of a partial clone tree is a key contribution of our work. We represent the partial clone tree in an ancestry matrix Z. An entry ZK equals 1 if subclone K is an ancestor of subclone K prime. Given this example, we have some 1s in our ancestry matrix Z. An entry ZK equals 0 if subclone K is not an ancestor of subclone K prime. It's possible to order the subclones in a way that a subclone with a higher index can never be an ancestor of a subclone with a lower index. Hence, we can automatically fill the lower left triangle of our ancestry matrix with 0. And given this example, we can also put in some more zeros in our matrix. An entry ZKK equals -1 if subclone K could be an ancestor of subclone K prime, but we're not sure about this, so we call this relationship undefined. Given our example, we have exactly 1 undefined relationships in our ancestry matrix Z. An alternative visual representation of this partial clone tree is this possible parent DAG, where we show when a subclone is a parent, not a parent, or a possible parent of another clone tree. Given a subclonal frequency matrix phi, for which a set of valid clone trees exists, the maximally constrained ancestral reconstruction, or short MAR, is a special partial clone tree that efficiently represents the uncertainty in the solution set. It defines the maximal set of all of the ancestral relationships shared by the solution set of clone trees, and leaves undefined all relationships that vary. Given the solution set of clone trees, it's trivial to build the MAR. However, usually the set is not given. This is why we developed SubMARine, our polynomial-time algorithm that, given a subclonal frequency matrix phi, approximates the MAR by constructing the subMAR. The subMAR is also a partial clone tree with the 3 important properties: that the subMAR is unique, its undefined ancestral relationships are a subset of those in the MAR, and hence all valid clone trees of phi are also completions of the subMAR. SubMARine defines ancestral relationships by propagating a set of validity rules onto the ancestry matrix Z. The first rule is the Germline Rule, which ensures that the germline, which is the root of the partial clone tree with an index 0, is the ancestor of all other subclones. Hence, we can set Z0K' to 1 for all subclones with an index K' greater than 0. The second rule is the partial tree rule that ensures that the partial clone tree has tree properties, meaning that each subclone can only have at most 1 definite parent and that the tree has to be transitive. In this example, subclone K is an ancestor of K' and K' is an ancestor of K double prime. Because we know that the tree has to be transitive, this undefined relationship between K and K' has actually to be a defined one, such that K becomes an ancestor of K double prime. The third rule is the generalized sum rule. This ensures that the frequency of a subclone K is at least as large as the frequency sum of its definite children K' for all samples n. This rule has 3 consequences. First, if we sort the subclones in descending order of their subclonal frequencies, we can derive trivial relationships, where a subclone K' cannot be an ancestor of subclone K if K' is larger or equal K. This explains the zeros in the lower left triangle of the ancestry matrix Z that we've seen on the previous slide. The second consequence is the crossing rule that is derived from the generalized sum rule. It states that a subclone K cannot be an ancestor of a subclone K prime if K has a larger frequency than K prime in one sample N, but a lower frequency in another sample N prime. And finally, the generalized sum rule leads to our subpoplar algorithm that propagates this rule in a more general way. For each subclone, the subpoplar algorithm checks whether the subclone can become a definite child of its possible parents without violating the generalized sum rule. If this is not the case, the possible parents are removed. If a subclone has only a single possible parent left, this possible parent is made its definite parent. The basic version of SubMARine takes the subclonal frequency matrix phi as input. It then builds the ancestry matrix Z, where initially all ancestral relationships are undefined. In a pre-processing phase, it introduces the Germline rule and sets the trivial relationships. In the first part of the main phase, it uses the crossing rule. Then the subpoplar algorithm starts that propagates the generalized sum rule and applies the partial tree rule. These rules are propagated until the Z matrix converged. Then it is output together with a possible parent matrix tau. Next to the basic version of SubMARine, we also implemented an extended version that takes subclonal copy number operations into account. In our work, we introduced the notion of a partial clone tree. SubMARine scales to a large number of subclones and efficiently represents uncertainty in the submar. SubMARine builds the submar by propagating validity rules for partial clone trees. You can find SubMARine on GitHub, and you can also have a look at our preprint on bioRxiv. And now, last not but least, I'd like to thank Jeff, Gunnar, Jens, and Quaid for working with me on this project, and thank you for your attention.